isn't it? But when you want to compare two data sets, they have to be under a common scale, isn't it? And to be under a common scale, the way to do it is to have it under an absolute scale. That means that the amplitude should be given as number of photons. Right? So now, how do you do that? Well, you really can't. I mean, for that you would need to have f000, because if you remember from the equation, everything depends on f000 times something. Okay, you would need to have f000, but where is f000? That's the direct beam. If you would collect that, you would destroy the detector. That's why you have the beam stop.
Oh yeah.
So that means that you cannot get it in an absolute scale without that. So what you do is you actually generate a model. So you generate the FC from your dark model, and for that one you can produce an f000. Okay? And then you use that to scale all the other data sets to the dark calculated model. And then they are all under an absolute scale. They're all perfectly comparable to each other.
Oh.
And with that, you can start to extrapolate, and you can start to do all the density integration analysis and so on and so forth. So that means that you can compare each time point. You see? But again, that's a bit of a more complicated situation. So I would say, wait for it. like when you're done. So yeah.
The password is.
Once everything is ready and you have the first part of the table 1, okay, and you know that everything is good.
It has.
Caps lock is on.
Oh.
Yeah, reading helps. So. You have it? I'm hoping tonight I can install Ubuntu and all the software and so on the Lenovo computer. So that means that we have a second laptop that can be used. So that, because if not, you're always, I get the feeling you're always fighting for the laptop, isn't it?
Yeah.
So hopefully we get an answer from the, what's his name? Mr. Tsai, and we get the new computers in here quickly. Also, maybe by tomorrow he hasn't said anything. Kevin, could you help Yuhei to send an email in Chinese? Because we all know this is one of those problems.
Send what?
Basically, you and me are looking for the new computers, and it's quite a lot of money that we're gonna spend on it. And I get the feeling, in many cases, what happens is they see something in English, they go. So if you could send tomorrow, basically write the same email but in Chinese. If they haven't responded by, say, tomorrow afternoon, okay, then I think with a bit of luck, or tomorrow lunch or something like that, because again, we're going to be spending about 200,000 NTD in new computers.
Ooh.
So what I mean is,
Yeah.
the guy should be interested in selling us that many computers.
Yeah.
So have you downloaded it?
Yep.
Okay, where are they?
I think yeah.
In downloads?
Yep.
Okay, so then let's move them in. Okay, so these are the ones, isn't it? So let's take them in and then we move them into install. Offsite, and we just copy them in here, isn't it?
Okay.
And so now we just open, so we go first for CCP4.
To
Okay.
truncate.
Exactly, and then we need to truncate them. Okay.
So we can do all at once.
Sorry?
We can do all our data set at once to truncate.
Well, yeah, we need to do one after the other.
Oh.
I mean, actually, it would be possible. You're absolutely right that it would be possible to write a script for this, but I don't think we needed enough to do a script every time. So, okay, I'm gonna go simply by time. You know, I start 8 picoseconds, then 60 picoseconds, then 600, then 3 nanoseconds, and 10 nanoseconds.
Okay.
Do you know what I mean? So that we have, so, and they are, very importantly, they are intensities without anomalous data. Okay? And ensure unique, and we copy it from the old dark. Okay? Okay? And so, sorry, let's write up here. This is 18 picoseconds, isn't it? So we can just run it. Then we go for 60 picoseconds. Okay? And we call it 60 picoseconds. And we run it. Then we take 600 picoseconds. Right up there, 600 picoseconds. And we run it. Then we take 3 nanoseconds, isn't it?
Yep.
And we're right up here, 3 nanoseconds. Okay? And we run it. It's so that you know what the hell it is each time. And then we do 10 nanoseconds? Yeah, isn't it?
Yep.
10 nanoseconds.
I'll change
And we
it.
change up here, 10 nanoseconds. The most important thing is this. Input data is intensities without anomalous data. Okay?
Okay.
That you need to keep like this, because it takes different kinds of input, and that's the one we want. Okay, so now we have everything. The next thing is we go and open Phoenix. Okay, and so you've done all dark, isn't it? And you've done,
But
so you're,
I think this one is not quite.
what happened with this one?
I just try to put the sidechain there.
Oh, okay. So
Yeah.
it's probably not very good.
Yeah,
So
not very good,
let's
I
take
agree.
this one for the
Yeah.
moment, isn't it? So
Yeah.
we take number 8. Okay, and so we go to difference maps. Okay, and now we click on maps here in crystals maps. Okay, and then in maps we generate the isomorphous difference map. Okay, and we're gonna do 18 picoseconds minus dark rough. Rough means that we haven't scaled it. So let's write it non-scaled. Okay? So our first file is always the one at the beginning. So it's 1 minus 2.
Or 1 minus 2.
Okay? So that means that we now take 1 should be 18 picoseconds, the truncated one, and 2 should be where is it?
Oh, you mean
all dark.
all dark.
Here, isn't it? No, all dark
Oh,
truncate.
truncate, yeah.
So that's what we want. Okay. Now the PDB for phasing is 8.
Well, I
Okay.
think that this is the new one. New one.
Sorry,
This one.
but this one you have modified. So no,
Oh, yeah.
The one that came out.
That's
So,
correct.
so and now you set it to structure factors, not to intensities. The comparison. Okay. Now the high resolution is the worst high resolution of the two. You have it up there, isn't it? So show me the table, and then we can take a look.
Not this one. 18.
Yeah, 18 picoseconds.
1 point.
1.53. So we write here 1.53 to 10. Okay. So why only to 10? We have more data. Well, the reason is that in general, the closer you are to the center, the higher the intensities.
Mm-hmm.
Okay? And so that means that in a way, what happens is that the low resolution data can completely dominate everything else. Okay? And then you see nothing about the side chains or anything like that. So that's why you cut it off to keep it relatively low. However, for extrapolation, you look at everything. Yeah? So, and then because you want a very nice and clean map, you set here your sigma to 3.0. So it means that you're only going to use structure factors that have an I over sigma of 3 or higher. Okay? So why 3 or higher? Quite simple. If you think about it, if you take 3 and do the square root of 3, okay, you get to about 2.
2, yeah.
So in that way, you're close to the standard setup. Okay? And then finally, you go to advanced options, and you go to you click on multi-scaling method. So what this will do is it will try to scale into each other. won't be super good, but it's better than nothing, okay? And so we run it. And then we can run the next one, which will be what, 60 picoseconds, isn't it? Here, we write 60 picoseconds, and we take this 60 picoseconds, this guy here, okay? And what's the resolution of 60 picoseconds?
Here.
1.55. That one, okay? And done. Then we do 600 picoseconds.
600.
And what's the resolution of 600?
1.53.
So we take this one,
Yeah.
and 1.53. Okay? And then we take 3 nanoseconds, isn't it?
Yeah.
We take 3 nanoseconds. What's the resolution?
1.54.
4. And then we take the 10 nanoseconds. What's the resolution?
1.50.
1.5. So simply 1.5. And then 10 nanoseconds. Okay, and now we have the data. So let's take a look. Wow, that looks pretty. That's a lot of changes already. So you can see it's 18 picoseconds. We can see movement of the arginine and movement of the aspartate. We can already see very clearly
Oh,
the movement of the asparagine. We can already see very clearly this movement around here, isn't it? And let's see, we can set it a bit higher, okay? So to clean up a bit, and so we can see here. So this is the, you can see this is the first tryptophan.
this one?
This one here.
Oh, this one.
This one is the first tryptophan. Okay, it goes from here to here, okay, and from here to here.
Second.
And you can see that around the second tryptophan there is already signal.
Oh.
You see? We don't see much of a change in the tryptophan itself, but we can see that these,
Oh.
they have moved. So that means that probably we have already a significant change going on around that tryptophan. Okay, so that the environment around the tryptophan has been modified here. If you remember, this should bring us so the 18 picoseconds, if I remember, is somewhere between these two.
I mean, the first and the second tryptophan.
Yeah.
And the first tryptophan to FAD, I think, is within 1 picosecond.
Yes, exactly. So that's why we can see that already here. Okay. Then we can take a look at the next one. So this is 60 picoseconds.